Then we have a great pleasure to invite Lyman-Werner from the Cosmos, ICG, UK. And Dan is actually a leading expert on the early universe, the first stars, and supernova and quasars. And he did a nice job, especially a seminal contribution to the understanding about the radiation feedback from the first stars and the supernovas. And then got a PhD from the UIUC, which allows know well. And later he got a fellowship position, postdoc fellowship position from the Los Angeles and from the Carnegie Mellon University and also the Heidelberg University. And at the end, he landed on the faculty position at the ICG. And today, Dan will be share his recent work on the first quasar in the universe. So let's welcome Dan's talk.
Well, thank you for the wonderful opportunity to talk to you again. I actually visited several years ago to talk about supernova explosions. And now I get to talk about the origin of the first supermassive black holes in the universe. And let me begin by saying that I have a very informal lecture and colloquium style. So if you want to raise a question on the spot during my talk, it's no problem to interrupt me at all. I'm happy to answer questions. So let's begin by saying, when we look at the centers of most massive galaxies today, we find supermassive black holes. And they range anywhere in mass from a few million to upwards of now 50 billion solar masses in some galaxies. Now, I would say there's, in the last 5 to 10 years, a new class of intermediate mass black holes has been discovered in dwarf galaxies. So Amy Rhines at Montana has done a lot of work on this as an astronomer. And these are typically 100,000 solar mass black holes in dwarf galaxies. So, but that is today. The universe is 13.8 or more billion years old, and those black holes have had a long time to grow. Beginning in 2003, we began to discover quasars, or actively accreting supermassive black holes, in galaxies at redshift above 6. And we knew they were above redshift 6 because we saw for the first time the evidence of the Gunn-Peterson trough in their spectra. So that was kind of a spectacular confirmation that the universe at a little above redshift 6 was still partly neutral, and that reionization of the early universe came to an end at about redshift 6. But even more shocking, what was shocking was the discovery of billion solar mass black holes at that redshift, which is less than a billion years after the Big Bang. And so, how billion solar mass black holes formed by such early epochs really posed severe challenges to our paradigms of structure formation in the early universe. So today, we've now found over 200 quasars above redshift 6, and we found 9 above redshift 7, including one at redshift 7.54, which is an 800 million solar mass black hole. And this is 650 to 690 million years after the Big Bang. So how these early black holes formed has been one of the leading questions in astronomy for the last 10 to 20 years. So let me go through what we think are the main pathways considered for their formation, for their birth. So the first that was looked at 20 years ago was that these early quasars simply formed from the black holes of population 3 stars. So primordial stars that formed in the universe at cosmic dawn around 100 million years after the Big Bang. So we don't know for sure what the masses of those stars were, because our telescopes aren't powerful enough to see individual primordial stars yet. Estimates are we have to have a 100-meter mirror on the ground to be able to see those objects. And even then, it would be tough because the near-infrared has to dodge water absorption in the atmosphere. But numerical simulations beginning in 1999 suggested that they were predominantly massive. The original simulation suggested that they formed in isolation, one per primordial halo. and they were predominantly a couple of hundred solar masses. But improvements in code, physics, and computer since then have shown that these stars can form in binaries, and they can form even in small clusters. And it's now thought that their masses were probably likely anywhere from a few tens of solar masses to a couple hundred solar masses. We'll come back to that in just a moment. Now, that's one possible channel. Now, that channel works, but only almost if you invoke miracles. And this is why. Even a 10 solar mass star, black hole, forming at redshift 20 to 25, can grow to 1 billion solar masses by redshift 7 if it accretes at nearly the Eddington limit the entire time down. So it works. We can make the math work. But that black hole has to be born actively accreting, and it has to accrete at nearly the normal kind of Eddington limit. Eddington limit really isn't a limit on the growth of black holes, but that's one that we commonly invoke, as kind of like a maximum rate at typical black holes, at which typical black holes can grow. Now, the problem with that is that it's almost impossible for these small black holes to accrete quickly enough after birth to reach 1 billion solar masses by redshift 7. And there are a couple of reasons for this. One, if the primordial star is just a few tens of solar masses, when it collapses and the black hole forms, often asymmetries in the central engine of collapse impart a kick to the black hole. And that kick can eject the black hole from its host halo at up to several hundred kilometers a second. And that kick ejects it from its own fuel supply and exiles it to the low-density voids between the halos and the filaments in the early universe. So it's very difficult for those really low-mass black holes to grow if they get kicked out, especially. Now, even if they don't get kicked out, once they start accreting, once they're born starving. In other words, the black hole itself forms in low densities. Why? Because the massive star is ionizing ultraviolet radiation boiled all the gas out of the host halo. And this happens almost in all halos. And so when the black hole is born, it's typically born in very low densities, number densities of 0.1 to 1 per cubic centimeter. And it's difficult for that black hole to grow quickly in such low densities. When its progenitor star boiled all the baryons, the gas out of the halo. So now, later, cosmological flows return gas to the halo, and the black hole is sitting there waiting for them. And it starts accreting. But once it starts accreting, the problem is that the X-rays start kicking all the gas out of the halo again. And so the initial growth of POP3 star black holes is very strongly self-limited. And the reason the gas gets kicked out again is not just because the X-rays heat the gas to high temperature. It's because the host halos have such low masses, the escape velocities from the halos are 2 to 3 kilometers a second. Sound speed in the ionized gas is 20 to 30 kilometers a second. So thermal expansion of the gas just causes it to boil out of the halo again at 10 times the escape velocity from the halo. In other words, the gravitational potential well of the host halo can't retain the gas once the black hole fires up. So again, I would say it's not impossible for POP3 stars to be the origins of the first quasars, but it's very difficult, and nobody has demonstrated it to happen yet. Final case in point on this. There was recently a simulation called the Renaissance simulation done with the ENSO code, AMR cosmology code. It looked at a 40 megaparsec cube of space, resolving the formation of 13,000 POP3 star black holes, and it followed their accretion rates. So doing that in a 40, think about how hard it would be numerically to do that in a 40 megaparsec box and resolve all the way down to the scales of accretion in that box on ordinary POP3 star black holes. It was difficult. They had to run that simulation on the most powerful machine on Earth at that time, which was blue tides. What happened was, out of those 13,000 black holes, only one did the accretion rate even approach an Eddington limit. And it wasn't even the Eddington limit, it was like a tenth of the Eddington limit, something like that. So even in statistics of large samples, it's hard to find just even one black hole that grows that quickly. Still though, not impossible, but nobody's found a way for it to happen yet. Okay, well, the next channel we can consider is the channel here on the right that we can collectively call direct collapse. And so in this picture, what happens is you get a primordial, you get a primordial halo forms. And the way to think about primordial star formation is the following. So how do primordial stars form in the early universe? Well, what happens is this. So 100 million years after the Big Bang, there's mostly only hydrogen, helium gas, right? Trace amounts of heavier elements. And so how many chemical reactions would you guess can occur in just primordial hydrogen, helium gas? And I'll give you a hint. Remember, in primordial hydrogen and helium, you can also have the ions, right? You can have H+, helium+, helium-2+, H-, H2+, and H2. H2 being molecular hydrogen, not ionized hydrogen. So in those 9 species, how many chemical reactions would you expect can occur in the gas phase? Because there's no dust in the universe to catalyze any kind of chemistry at this point, not like in the galaxy today. So anybody want to venture a guess?
Definitely molecular hydrogen.
Huh?
Molecular hydrogen formation.
All formation, all chemical reactions, including those that form molecular hydrogen. Over 400. There are over 400 chemical reactions that are possible in primordial gas. But the ones that we're most interested in are the ones that govern the formation and destruction of molecular hydrogen. Because molecular hydrogen is the only coolant that can operate below 10,000 Kelvin to cool primordial gas. Hydrogen can also cool primordial gas, but it has to be at 10,000 Kelvin to have enough collisional energy to activate that n=1 to 2 transition, that Lyman alpha transition that emits that ultraviolet, that Lyman alpha photon that carries energy out of the gas, allows the heat of varialization to be carried down to the cloud to continue to collapse. That only happens above 10,000 Kelvin. So this is the way we think of primordial star formation in the community. A primordial halo, when it reaches 10 to the 5 solar masses, or a few times 10 to the 5 solar masses, it will form a primordial star unless something prevents it from forming one. And why will it form a primordial star? Because at that mass, the potential well of the halo is deep enough to congregate gas to high enough densities to elevate through chemistry, 2 body reactions typically, the H2 mass fractions up to a few 10 to the -5. And once you have H2 mass fractions of a few times 10 to the -5, that's enough to cool the gas and allow it to collapse into a star. Not quickly. Think of it as a subsonic or transonic settling flow. It's not like the supersonic collapse that you find in cold, dusty molecular cloud cores in the galaxy today. Pop-3 star formation was a much more leisurely process. And so the gas would settle in bit by bit until central densities exceeded 10 to the 8th per cubic centimeter. Then molecular hydrogen formation would explode through 3-body production of molecular hydrogen. The core of the cloud fully molecularizes in just a couple of years. That's like pushing the gas over the cliff. It collapses and forms a star. Okay. Now, what can prevent it from forming a star? Well, nearby pop-3 stars. Because if you have a halo that's growing through mergers and accretion from filaments, like this, let me skip that slide, I'll come back to it in a second. Here, this is a simulation box, 128 kiloparsecs on the side. And what you're seeing is dark matter collapsing into this, perhaps for you, familiar cosmic web of filaments and halos. So you see the the filaments, and you see those bright dots, which are halos, and you see this brightest dot in the center, where all the halos are congregating into a massive halo. In that simulation box, that halo in the center is the first to form a primordial star. So it's accretion and mergers with other halos that allow these stars, these halos, to grow to a few times 10 to the 5 solar masses. Well, what if this process happens nearby another cluster of Pod3 stars? Well, being several tens at least of solar masses, they have a large ultraviolet output, and they put out a lot of what we call Lyman-Werner photons. Lyman-Werner photons are line photons. They reside within 78 bands between 11.2 and 13.6 electron volts. So because they're less than 13.6 electron volts, that they don't ionize hydrogen, but they crack molecular hydrogen apart through photodissociation process. It's a two-step Solomon process. And so nearby stars can sterilize that halo of molecular hydrogen. Well, no molecular hydrogen, the gas can't cool and form a star. So what happens is the halo keeps growing and growing and growing in mass until it reaches about 10 to the 7 solar masses. At 10 to the 7 solar masses, the gravitational potential well is deep enough so that when gas falls to its center, it's heated to 10 to the 4 Kelvin. And that's the magic number. That's one of the magic numbers in astrophysics, right? Because that's the temperature in hydrogen at which you can start to activate the N equal 1 to 2 transition. Well, let me go back. At those temperatures, if the gas starts cooling by Lyman alpha emission, Lyman alpha cooling is 10,000 times faster than molecular hydrogen cooling. And what happens is a catastrophic collapse of gas to the center of the halo, proto-galaxy or nascent halo. And that gas collapses to the center at rates of up to a solar mass per year. And the idea is that those flows build up a supermassive star. The supermassive star grows, has a short life, then collapses to a black hole with a mass of 10 to the 4 to 10 to the 5 solar masses. Now, that pathway is a lot more attractive for forming a quasar by redshift 7 for a couple of reasons. So first, instead of being born at a few tens or hundreds of solar masses, it's born at 10 to the 4 to 10 to the 5 solar masses. So Bondi-Hoyle accretion rates scale by mass squared. So the maximum Bondi-Hoyle accretion rate is much higher for one of those black holes, and they can accrete at much higher rates and grow at much higher rates than less massive objects. Second, they're born in very dense environments because of catastrophic baryon collapse. And so they're not born starving, they're born in the very accretion flows that grew the supermassive star in the first place. Now, some might ask, well, in normal Pod3 stars, the star was bright enough to boil all the baryons out of the halo. Well, wouldn't a supermassive star be even more effective at that because it's 100,000 solar masses? It turns out no, because the faster a supermassive star grows, the cooler and redder it is, it turns out. As I'll come back to a little later in the talk, these supermassive primordial stars were bloated red cool hypergiants with surface temperatures of about 5,500 Kelvin, regulated by H minus opacity. They evolved along something called the Hayashi limit. And because of that, they had very little ionizing UV radiation output. They were bright, they could be 10 to the 10 solar luminosities, but it was cool radiation, not hot ionizing radiation that could heat the gas and kick it out of the halo. Even better, once these direct collapse black holes start accreting and firing out X-rays, these are 10 to the 7 solar mass halos, not 10 to the 5 solar mass halos. They have much deeper potential wells. They can retain the gas against X-ray heating. So these halos don't allow the host black hole to kick the gas out, even after they start emitting X-rays. So that's the idea. Those are the reasons why most people in the community today think that the formation of supermassive primordial stars in atomically cooling halos may be the origin of the first quasars. In fact, that's been thought for over 20 years. What I'm going to show at the end of my talk is that we were wrong the whole time about that process. And I'll come back to why towards the end of my talk. Now, it doesn't mean that this process didn't happen in the early universe. Our cosmological simulations show it certainly did. It was a robust process. And probably there were a lot of intermediate mass black holes forming by redshift 15. And it could be that the universe, it could be that James Webb and Euclid and the RST will find these objects because they'll be powerful enough and sensitive enough to detect these objects at high redshift. So the advent of these telescopes is going to really open a fascinating era in early universe black hole astronomy. But all I'm saying is it turns out this almost certainly wasn't the process by which the first quasars formed. We were wrong for 20 years. Not in a bad way, but it was just incorrect. Now, there's a third paradigm for the formation of the first quasars that I should talk about, that I should touch on. And this is the merger-driven supermassive black hole scenario. And this is what happens. So in this scenario, you have two protogalaxies colliding at about redshift 8 to 10, typically. And Lucio Meyer and his group at Zurich found years ago, starting about 10 years ago, and they started with very idealized protogalaxy structures, but have now shown this to happen in actual cosmological simulations. What happens is two of these protogalaxies collide, and in certain cases, gravitational torquing between the two cores can slingshot gas into their center of collision at rates of up to 10 to the 4 solar masses per year. And at those rates, what happens is what forms is what they call a supermassive nuclear disk. And this supermassive nuclear disk has a radius of a few parsecs at the center. So think about it. So in just 10 to the 4 years, you can build up 10 to the 8 solar masses of gas within just a sphere of just a few parsecs in diameter. And so the question is, well, what happens to that gas? What's the fate of it? What they find, they can't simulate it because it's below the resolution limit. So they don't know for sure. But what they hypothesize, and they have some physical basis for supposing this, is that bar instabilities form within that dense nuclear disk that shed angular momentum and allow the gas to collapse to higher and higher densities. And it becomes, at some point, so dense that it becomes subject to the radial general relativistic instability. And the general relativistic instability can cause that gas to collapse to a black hole without forming a star. So in that case, that is true direct collapse if you think about it, because the gas directly collapses into a black hole in that scenario. And they think that they can account for black holes of up to 10 to the 8 solar masses at redshift 8 to 10. And then subsequently that black hole grows into a quasar by redshift 7. So I won't comment much on that except to say, so far, actually I was the reviewer on their last paper, and so far, I think the only remaining question is they really have to show what truly happens to that supermassive nuclear disk at the center of the protogalaxy. But I think that in principle that could work. The difficulty is how do they attach that process to the demographics of redshift 6 quasar formation? Because right now, the current demographics is about 1 redshift greater than 6 quasar per cubic gigaparsec of space. So these are relatively rare objects. How can they tie this process to those numbers? That's kind of one of the main questions right now, I think. But it has to be included, and I think it's a very interesting potential channel for early black hole formation. Okay, so I'm going to skip over those slides because I kind of talked about them. But let me just play this movie quickly. So what we're seeing here is the formation of a primordial protostellar disk. And for those of you can see, these little white crosses that form are dense cores that are thought to collapse into stars within the disk. This is from an SPH, smooth particle hydrodynamic simulation done about 10 years ago, roughly 10 years ago. And as you can see, the total evolution time is only 1,300 years in the simulation. And I put this simulation up to show that, in spite of over 20 years of really heroic numerical efforts, we still don't have a firm handle on the masses of the first stars in the universe from numerical simulations. And that's because, in part, we're still excluding some important physics. For example, we don't have magnetic fields in these simulations. And magnetic fields are thought now to arise through subgrid turbulent dynamo processes in primordial protostellar disks. And we don't even have all the radiation physics in the simulations that can exert important feedback effects on the final masses of the stars. So I'm not discouraged by this. I think that when I look at this, I see many good future PhD projects. And that's the way I look at it. The downside is we don't have firm, firm predictions of what the primordial initial mass function is yet. But right now, the thinking of the community is a few tens to a few hundreds of solar masses. Okay, so let me reiterate this atomically cooling halo scenario. So, as I mentioned, in this picture with supermassive primordial stars, through accretion and mergers, a halo reaches about 10 to the 7 solar masses without having formed a star, and that requirement is crucial. This halo cannot have formed a star, because if it did, and that star blew up and seeded the gas with heavy elements, that gas would cool and fracture on much smaller mass scales. And you wouldn't get a single supermassive star forming in that halo. You get like a cluster of much lower mass stars forming. If that gas was pre-enriched by even one supernova explosion or 2 supernova explosions. So how do these halos, how can a primordial halo grow to 10 to the 7 solar masses without forming a star? Either, like I just mentioned, that halo grows in the vicinity of other primordial stars that destroy all the molecular hydrogen in the halo and prevent it from cooling. Or there's another possibility that I didn't discuss, and that is supersonic baryon streaming motions relative to dark matter in the primordial halos. And the way that works is, I think most of us have probably heard or are familiar with baryon acoustic oscillations in the primordial universe. Baryon acoustic oscillations left many early primordial halos with sloshing motions between the gas in the halo and the dark matter in the halo. And we call that supersonic baryon streaming motion. And that sloshing motion between the gas atoms and the dark matter was violent enough to prevent gas from collapsing into a star, even if molecular hydrogen is present. Even if that halo isn't in the vicinity of other stars. It might form molecular hydrogen, that molecular hydrogen might cool the gas, but there's just too much sloshing motion for any kind of organized collapse. Okay, yes?
In the first scenario, I'm assuming you already considered, but does H2 significantly self-sheet itself in the sense that?
Excellent question. And the answer is, so the question is, let's say a primordial halo forms in the vicinity of nearby stars. So if you think about it, molecular hydrogen forms fastest at the center of the halo because that's where the densities are highest. And H2 formation is a two-body process, so it's proportional to density squared, at least at early times. And then, so could it be that enough H2 forms at the center of the halo to shield itself, at least in part, from external Lyman-Werner photons coming in? The answer is yes, it can. And in fact, recent simulations done by my student Sam Patrick have shown that only in the most extreme Lyman-Werner backgrounds is all the molecular hydrogen destroyed. In more moderate Lyman-Werner backgrounds, which were hundreds of times more common in the early universe, what you would get is the halo would the gas would be in a multi-phase state.
Yeah.
So basically, in the outer regions of the halo, you have hot atomically cooling gas, but you have an island of cold, a cool molecular hydrogen disk that's a few hundred degrees Kelvin in the center of that hot 4,000 to 8,000 degree Kelvin gas. And then in that case, what happens is you get star formation intermediate in mass between pure pop-3 star formation and this truly supermassive primordial star formation. Those that multi-phase medium creates stars that were likely a couple of thousand solar masses, not 10 to the 4, 10 to the 5 solar masses. So I'm glad that you asked your question, because we now think that there were really 3 primary channels of primordial star formation in the early universe with very distinct mass ranges. A few tens to hundreds, a few thousand, and then 10 to the 4 and above. And they're very distinct.
In the intermediate phase also, I mean, that also will form a black hole very soon. Because
Yes.
Yeah. So.
Yes, and those black holes can have masses of a few thousand solar masses. It turns out that, at least in the simulations performed so far, that's not mass enough to produce a redshift 7 quasar. Because you have to be up at least a few 10 to the 4 to 10 to the 5. But I'll come back to that in a second when we talk about the cosmological simulations. Okay, so as I said, but when the halo grows to a few 10 to the 4 solar mass, so 10 to the 7 solar masses, as virial temperatures reach 10 to the 4 Kelvin, you get atomic cooling. That causes gas to crash to the center at high rates. And before 2013, we weren't really sure about the fate of that gas. So in the movie on the right, you're seeing atomically cooled flows crashing to the center of the halo, and it forms a supermassive primordial disk. And that primordial disk, that star-forming disk, can be a couple of parsecs in diameter. But these are atomically cooling flows. So, and as you can see, the accretion rates here, over time, over a couple of mega years, range from 0.1 solar masses per year to close to a solar mass per year. And so before 2013, people couldn't say definitively what happened to that gas. Did it form a supermassive primordial star with a short lifetime? Or did you just get a denser and hotter core that later became subject to the general relativistic instability and then got enveloped by an event horizon? You had the formation of a black hole without an intermediate star phase. And so what happened is that stellar evolution calculations starting in 2013 showed that that gas produced supermassive primordial stars. Now, it used to be thought that in the early simulations, the first of these simulations was done back in 2008. And even in 2009, and even to the mid-2010s, everybody thought that atomic cooling produced monolithically a single supermassive star. But they thought that because none of us was evolving the disks for long enough dynamical times, for long enough evolutionary times. And when we followed the evolution of those disks for longer times, we found after 500 kiloyears, almost all of them fragment into supermassive fragments. So now it's thought that supermassive star formation likely occurred in multiples. Certainly, in some cases, certainly binaries, like in the halo along the bottom, certainly binary supermassive stars form. And of course, that's interesting, because if they form in close enough vicinity or proximity to one another, and likely merge, as they likely will merge on fairly short time scales because they're forming in high densities that would create a lot of radiative drag effects that would cause end spirals. Then there's a chance that of course, LISA will pick these up, would pick up DCBH mergers at high redshift. And initial calculations have already shown that LISA will be more than sensitive enough to pick these up at redshift 15, even 20. So we now think that supermassive stars probably formed in binaries or small multiple systems like this. Then, as I mentioned earlier, most of these stars, especially the rapidly accreting stars, ironically are cool red bloated hypergiants. And in fact, their radii may extend out to Neptune's orbit, the equivalent. These were large objects, cool diffuse objects that formed at high redshift. And so now at lower accretion rates, so recent calculations by my student Nick Harrington showed that stars accreting at rates below about 10 to the minus 2 solar masses per year, so less than 0.01 solar masses per year, they didn't evolve as cool red objects, they evolved as hot compact blue objects. And those stars could put out a lot of ionizing radiation that in principle could affect the accretion inflows onto themselves. So to get the true masses of those supermassive stars, you have to have radiation hydrodynamics turned on in your cosmological simulations, because ionizing UV outflows from those stars could slow down accretion onto themselves. However, we have now performed those simulations, and they show that while accretion rates might slow down onto those stars, they're still massive and they still produce supermassive stars. Just not 10 to the 5 solar mass stars, but maybe a few, maybe 10 to the 4 to a few 10 to the 4 solar mass stars. So, what are the prospects for detecting supermassive stars as the seeds of the first quasars? And the answer is, even with James Webb, it would be tough. With James Webb, you could probably see a supermassive primordial star at redshifts of, I would say, 8, really pushing it 10, unless they undergo pulsations. If they pulsate and frequently re-brighten and dim, we might be able to detect them as transients, perhaps even out to redshift 15. A recent paper showed that. But detecting the primordial star, the supermassive primordial star itself, is a little difficult, but not impossible, especially if you have, and I should change this to RST, especially if you have RST. Because here's the thing, James Webb is a super sensitive instrument, but it's a pinpoint instrument. Its field of view is so small that that it might have a hard time even just coming across a primordial supermassive star, depending on the search pattern. The nice thing about the RST and Euclid is they have enormous search areas. And now they're less sensitive. They're not as sensitive as James Webb, but their enormous search fields contain thousands of massive galaxies and galaxy clusters that can act as gravitational lenses that boost flux from background supermassive stars to above the detection limits of RST. So it is possible that RST and Euclid will detect lens supermassive stars. There's a recent ASIAA letter out on this. So it's possible. We'll have to devise the searches for it. Also, direct collapse black holes could emit radio. So we use these fundamental planes of black hole accretion that people have built up from quasar observations to estimate the radio flux from a direct collapse black hole. And it turns out that that even with SKA, in fact, the SKA final survey or typical surveys by NGVLA would have a hard time picking up direct collapse black holes above about redshift 10. So we won't be able to see the birth of the first quasars with radio, but there might be other possibilities. Okay, so let me go into now a cosmological simulation. So my former postdoc at Los Alamos, Joe Smith and I, developed a cosmological simulation that showed for the first time how a redshift 7 quasar could form. Let me give you a bit of background. Since about 2012, Tiziana Di Matteo's group at Carnegie Mellon have been working on very large box galaxy formation simulations. So these are typically half a gigaparsec boxes. And one of her interests in particular was to try to tune the physics in that box to try to get, to see if she could get the formation of quasars by redshift 6 in her simulation box. And what she found, and there were a couple of surveys that she did. One was the massive black simulation, then there was massive black 2, and then there was blue tides done on the blue waters machine, anyway, at Illinois. And what she found was that in these gigaparsec boxes, roughly, there are about a dozen or 2 dozen reservoirs of gas capable of fueling the rapid growth of a direct collapse black hole after it formed. See, forming a massive seed doesn't guarantee that you'll get a quasar. That seed then has to grow very quickly to reach 1 billion solar masses by redshift 7, and you have to have a gas supply capable of fueling that without major interruptions along the way. What her simulations found, and others have confirmed, have now confirmed, is that you can get redshift 6 or 7 quasars in very special gas reservoirs, halos. I don't think I touched anything over here. Thank you. Maybe that was the machine giving me a message. Anyway, so this is what they found. They found that the sites of redshift 6 quasar formation were rare halos that grew to 1 trillion solar masses, over 10 to 12 solar masses, by redshift 6. And they grew primarily through accretion, no major mergers. So that resulted in gas collecting in these halos in low shear environments that allowed the black hole to grow quickly. Does that make sense? So, but that's tough for simulators. And this is why. In her half gigaparsec box, the highest resolution she could achieve in her original simulations was 1 kiloparsec. That doesn't even allow you to resolve the structure of the gas within the host galaxy of the quasar, right? So this is what we did. What we did was we sifted through several hundred 100 megaparsec volumes of space until we found a halo that did reach 1 trillion solar masses by redshift 6. In our case, it was redshift 7, actually. And it was primarily through accretion and these cold accretion flows, not mergers. Now, 100 megaparsec box allowed us to zoom in with AMR techniques down to about 30 parsecs. Not enough to resolve accretion on the black hole, but we could resolve star formation within the host galaxy of the black hole. So this is what we did. We then took that box and we evolved it down we resimulated it with all the gas physics down to the point where that halo reached 10 to the 7 solar masses, and at that mass, or a few times 10 to the 7 solar masses. And at that mass, we dropped a 10 to the 5 solar mass direct collapse black hole in. So we simply assumed a direct collapse black hole formed. When the halo reached that mass, we couldn't demonstrate that it formed. We simply assumed it did. Now, that's what everybody did. In all of these massive galaxy simulations you've heard about, like the Eagle, Illustris, Millennium, massive black, blue tides simulations, they have a simple algorithm that once the halo crosses a certain mass threshold, they just put like a large black hole in the center. They don't account for how that black hole formed. They just assume it did. So anyway, what we then did, and this is what that halo looked like at redshift 7. As you can see, these powerful accretion streams here were fueling its massive growth. So what we did was we put a 10 to the 5 solar mass direct collapse black hole into the center of that halo, and then we turned on X-rays from the black hole. So we assumed a single photon energy of a KeV. We used adaptive ray tracing transport with the Mori code. We had up to 10 levels of refinement. We reached a resolution of 30 parsecs. We couldn't resolve flows onto the black hole, so we used an alpha disk model to approximate. It's a subgrid approximation. It's standard. People actually usually use Bondi-Hoyle, which we think wasn't as good as the alpha disk model, so we used the alpha disk model instead. And then we included stellar winds from star formation, their supernova explosions, and ionizing ultraviolet radiation from the stars forming in the vicinity of the black hole at later times. And that's really the difficult part of the simulation, is getting the feedback right. Because once stars form in the vicinity of the black hole, their ionizing UV radiation can suppress flows onto the black hole. Their supernova blast waves can rattle the interior of that host galaxy and either promote or suppress flows onto the black hole. And we wanted to have all of that physics in the simulation. So here's the direct collapse black hole birth. You see X-rays coming out, and here's our approximate spectrum that we used. The direct collapse black holes we found would be detectable in the near infrared by James Webb beyond redshift 20. So if we wanted to hunt for the seeds, the first quasars, the direct collapse black holes are what you want to look for. Their supermassive stellar progenitors are harder to capture. But you can capture the direct collapse black holes pretty straightforwardly with James Webb, with lensing, with Euclid, and RST with lensing. So here's the growth of the H2 region of the quasar at redshift 17. It's pretty small. Redshift 9.5, bigger, but still pretty small. But then by redshift 7, it's suddenly grown to 2 megaparsecs in radius. So why the sudden growth spurt? It simply comes from the exponential nature of Eddington rate accretion growth. So you can do a quick back-of-the-envelope calculation to show that if a black hole is growing, for example, at half the Eddington limit rate, that its mass is exponential with time. As you know, exponentials are flat until they explode. And this is why the H2 region suddenly grows large at redshift 7. In this simulation, the black hole reached actually 2 billion solar masses by redshift 7.1. That was a good agreement, good match to the Morlock quasar. Redshift 7.1, 2 billion solar masses. Here you can see the error bars on that measurement. And this is what we were really also happy about. People have measured star formation rates in the host galaxy of that redshift 7.1 quasar. And they measured the star formation rate to be about 250 solar masses per year. And ENSO matched that at redshift 7.1. So that gave us, that was a good sanity check for us because it showed us that we're getting the basic feedback in the host galaxy of the quasar, right? And then the radius of the H2 region of our quasar, the quasar proximity zone for J1120 from our simulation matches that from that quasar. And this is another nice thing where we lucked out, I think, and that is that observers had measured supersolar metallicities for the host galaxy of that quasar. And that was surprising to many because, remember, this is a redshift 7.1 galaxy. And the host halo is already at 1 trillion solar masses, and it's already at supersolar metallicities because of vigorous star formation at high redshift. And we matched those metallicities in our simulations. So our simulations predicted also that we would get strong chemical enrichment. So really quickly, published this data yet, but we looked at the H-band AV magnitudes of this quasar in our big box simulation. And what we found was that out to redshift 13 to 14, that Euclid would be able to detect this quasar. And that's good news for us because we need the wide fields of Euclid and RST to harvest these objects because they're relatively rare. And the fact that they're bright enough out to even like redshift 12 to 13 to 14, it will help us probe the growth of the first supermassive black holes to much earlier epochs than we can do now. Yes?
How would these measure as compared to other supermassive black holes formed from other processes, not from the direct collapse?
So, so I think your question goes to how can these measurements discriminate between formation pathways? Yeah. So, for example, if we detected something like this with Euclid, black holes forming today wouldn't be visible. Almost certainly wouldn't be visible because they wouldn't have masses that were high enough. Not at these redshifts. So at these redshifts, the only black holes that would be forming are either through these rapid accretion processes that I've been talking about in the simulation, or perhaps the merger-driven growth paradigm. Now, here's the thing about the merger-driven growth paradigm. I don't think that paradigm would produce a black hole like this at redshift 14, because their protogalaxy mergers all happen down around 8 to 10. I don't think they can get massive enough collisions at redshift 14. So if we discover these objects at redshift 14, that doesn't rule out the merger-driven scenario, but it does tell us that most of the first quasars we're seeing were probably through cold flow accretion processes and massive sea formation. Okay, so one more comment, and then I'll get into the last couple minutes of my talk. And that is, we have new calculations we just submitted to monthly notices that show if we assume the fundamental planes of black hole accretion are valid for these early quasars, that SKA and MGVLA would be able to detect a quasar like J1120 at much earlier stages of its evolution, even down to back to redshift 14 to 15. And that's nice because for a couple of reasons. First, detecting these objects in the near infrared will be possible, but we'll have to initially do photometric detections, right? So we'll do like band dropout detections. If we did a radio follow-up and we found radio emission coming from that same object, cut and dry is a black hole. Because we wouldn't expect radio signals that strong from just very active star formation in an early galaxy. That's one thing. The other thing is that just in general, these radio observations could just be a separate way. We could run separate radio surveys looking for these objects, and whether a near-infrared survey or a radio survey turned up a candidate, we could then use the other to confirm what was going on. So I think radio detections in the coming decade of high redshift quasars, they'll all be part of this redshift 5 to 15 era of quasar astronomy that I think is now upon us, basically. It will definitely be upon us when Euclid is launched and W first is launched in the coming decade. Okay, so my only comment on this slide, you can read the bullet points yourself, but the way I think about it is James Webb and the ground-based ELTs will be very sensitive but very narrow. The RST and Euclid will be wide but less sensitive. So I think we can do photometric identifications with Euclid and W first, and then very detailed spectroscopic follow-ups with James Webb and the ground-based CLTs to really nail down the properties of these objects and discriminate them from other interlopers, for example, in color space. So I think that there'll be very lovely synergies between James Webb and Euclid and RST in the coming decade in hunting for these objects. All right, now, as advertised, the last really short part of my talk. Okay, I mentioned earlier that the first simulation of an atomically cooling halo was done in 2008, right? But here's the key. And then there have been dozens of papers on atomically cooling halos and accretion flows and direct collapse black hole formation since then. And we published some of them. So some of those came from our group. But what we've known, what we realized, actually, my group realized several years ago was none of those halos, atomically cooling halos, are destined to become a quasar at redshift 7. Why? Well, it's because the massive black simulations in 2012 started showing us what kind of halos could produce those redshift 7 quasars. What kind of special gas reservoirs could rapidly fuel the growth of those direct collapse black holes. And they were very different than any of the halos that we had simulated in our small boxes up to that point. Even the Renaissance simulations with ENSO, which had that 40 megaparsec box, a 40 megaparsec box on average would not be expected to hold even one of these reservoirs of gas. But the problem is, and this was the really hard problem, the problem is, okay, we can pick out one of these special halos that we think will form a quasar by redshift 7, but we couldn't zoom down to small enough scales to rule out the formation of normal primordial star formation in those halos first, before a supermassive star formed. That's the key, and let me repeat it, because that was the key problem. The key problem was, sure, we could pick out one of these special halos, and those halos were very different in character, I'll come back to why in a minute, from the normal atomically cooling halos we've been simulating for 15 years. Yes, we can pick out one of those halos, but we need really big boxes to find one in a gigaparsec volume. And in those really large boxes, it's really hard to zoom down to scale small enough to rule out that halo wouldn't form a normal star first. And if it formed a normal star first, game over. Then we can't prove yet how a quasar was born in that halo, right? Until a few improvements came along in the ENSO code a couple of years ago. And what we were able to do is, using a 37 megaparsec box, we did capture one of these halos, and we were able to resolve down to mass scales of 1,000 solar masses. And that's key, because that allowed us to resolve this halo when it passes 10 to the 5 solar masses. Remember, that halo grew from a small mass to a large mass. If we could resolve the halo at 10 to the 5 solar masses, we would know if a star formed in it at the earliest stages it could form. And that's what we did. So we simulated this box at super high resolution, and we took our numerical lumps, by the way, in doing that in terms of computing time. But we are able to follow the growth of that halo past 10 to the 5 solar masses, 10 to the 6 solar masses, up to 10 to the 7 solar masses, which is when it first formed a star. But why didn't it form a star at 10 to the 5 solar masses, or 10 to the 6 solar masses? This is why. This is a special halo. It reaches 1 trillion solar masses by redshift 7. How? It's being pounded by these cold accretion streams. It's at the nexus of these very, very strong, very rare cold accretion flows. It's these nexuses that are only a dozen or 2 dozen per cubic gigaparsec. We found that the halo, there were no primordial stars in its vicinity at all. There was nothing around it. It was just the halo, but being pounded by those hard accretion flows. So the gas formed molecular hydrogen, great, no problem. 10 to the 5 solar masses. It had a large molecular hydrogen fraction. and the gas could cool and did cool, but it didn't collapse. Why? Because of turbulence. Those accretion flows were pounding the halo so powerfully, they kept the gas really turbulent. In fact, the turbulence prevents that gas from collapsing until the halo reaches a mass of a few 10 to the 7 solar masses. Why could it then collapse at a few 10 to the 7 solar masses? Was it because of atomic cooling? No, it turns out the halo is too cold. At a few 10 to the 4 solar masses, the halo is only 1,000 or 2,000 degrees Kelvin because it was very efficiently cooled by molecular hydrogen. It simply hadn't collapsed because it was so turbulent. What allows the gas to collapse is the gravity of the halo. The escape velocity from the halo, the infall speed of the gas, exceeded the turbulent velocity and simply crushed the gas down to high densities. Let me show you some plots quickly. So see, at early times, if you look at these plots here, turbulent gas velocities exceeded the infall velocities until later times. When the halo reached, so for a long time, the turbulent halo gas velocity was 30 kilometers a second roughly. Infall velocities were a lot lower than that until the halo reached a few 10 to the 7 solar masses. Then the infall velocities exceeded those turbulent gas velocities and simply crushed the turbulent gas down to high densities, at which it could then collapse and begin to form stars. But when it did, those collapse rates were very high. So let me show you some pictures here. So this is a 100 megaparsec image, 0.1 megaparsec image, so you can see the formation of the dense core. Sorry, 10 parsecs. You see the core of the halo here, high densities. Then you see one of the cores, 2 cores form actually. Here, this is on a scale of a 10th of a parsec. This is a 10th of a parsec. And then when we resolve all the way down, you see a disk beginning to form around that core. And that's where a star first begins to form in the halo. So let me show you really quickly a movie. So as you can see, remember earlier I showed you the formation of an atomically cooled disk? It was like a parsec or 2 in radius, with the formation of a single dense object in the center, maybe a couple of objects. This gas is way too turbulent for any organized structures like that to form. What instead forms are a couple of dense clumps. That's it. No accretion disk at large radii, just a couple of dense clumps. And it turns out that I think one of the clumps was down here. You can see a red dot here. Another one, I think the other one was up here. And as those objects those 2 clumps, they accrete not as rapidly as purely atomically cooled disks accrete, but still at quite high rates. So anywhere from 0.01 solar masses per year to a few tenths of up to, in certain cases, there were episodes of half a solar mass per year. So we were very fortunate at the time, because right around the same time, we were able to develop and successfully carry these cosmological simulations out. My student, Nick Harrington, developed the ability to evolve the stars in the MESA stellar evolution code. And he found that, that these stars don't evolve as red-bloated hypergiants. They're typically hot blue stars. They kind of go back and forth between cold states and hot states, but they spend most of their time as hot stars. But one of those stars reached 30,000 solar masses. The other star reached 40,000 solar masses. And so, in conclusion, it turns out we were wrong for 20 years about how the seeds of the first quasars formed. It turns out that the only halos capable of forming a quasar by redshift 7 made their own seeds without any need for unusual exotic environments like strong Lyman-Werner backgrounds or supersonic baryon string motions. None of that was necessary. The existence, in other words, of redshift greater than 7 quasars was simply a natural result of cold dark matter cosmology. So the reason this result was published in Nature, I think in part was because our two judges were large-scale galaxy formation people, and they were really happy that our simulation showed that what they've been doing by faith for like 20 years was the right thing in the end. I think politically that's why our letter got in, our result got into Nature all the way. That's just my own opinion, I don't know for sure. But here's another really nice result of the simulation. So not only did we show that the few gas reservoirs capable of building a quasar by redshift 7 made their own massive seeds. That means that the number of redshift 6 quasars ultimately is tied to the number of reservoirs at high redshift. And in the large-scale cosmological simulations, we find, around a dozen to 2 dozen reservoirs per cubic gigaparsec. That's within an order of the magnitude of the number of quasars we've already found at that era. Now, if you look at the number of direct collapse black holes formed at that, at redshift 20, it's orders of magnitude different from that demographic, right? There's no way to tie the demographics of direct collapse black hole formation and topically cooling halos to the number of halos we see at redshift 7. And also, by the way, it's really kind of hard to fine-tune the atomically cooling halo scenario in the first place. And the odds of getting a small group of stars close to 1 halo per cubic gigaparsec or a dozen halos per cubic gigaparsec is just not going to happen. So those other pathways we examined, because we said, well, this is a way we can make massive quasar seeds. But what wasn't really being admitted was that this is never going to work, because how can we pair these exotic environments to the much rarer halos required to fuel the subsequent growth of the black hole to 1 billion solar masses by redshift 7. So we think know how quasars were born, the redshift 7 and 6 quasars were born at high redshift, and we think we now understand their numbers at high redshift. And that's the end of my talk. Thank you.
Thank you very much, Dave. Any questions for this talk? Anyone?
Thank you for your talk. I have 2 questions. The first one is I missed this part, so I wonder in your simulation, do you need to assume initial mass function or something for the stars?
No. What we did was we simply followed the growth of the clumps in the halos. We could do that with a cosmological simulation. And then we simply took those accretion rates and plugged them into our stellar evolution calculation. And we showed the stars that those clumps would become.
Okay.
Now, the only thing that we weren't self-consistent about was we didn't include radiation from the blue stars in the halo that could have altered their accretion rates, but we have other simulations that showed that it wouldn't be a strong effect. So the massive seeds would still form.
Okay, thank you. And my second question is about, this kind of mechanisms you just described, I wonder whether or not it will also impact the way of galaxies formed or evolve at early universe?
Well, yeah, so we focus mostly on these very unusual structures that form by redshift 7, and they really are outliers. What I'd like to know is the processes that, I think that we need to do a lot more work on the processes that created or originated the black holes that reside in most galaxies today. And that's what the large-scale galaxy formation people are trying to do, but they just don't have the resolution to capture the origin details. So I think we have more work to do.
Thank you.
Yeah.
Well, in your early universe, you form supermassive stars. But in my recent universe, we form superstar clusters.
Mhm.
So each superstar cluster has a mass about 10 to 14 to 5 solar masses. And so why, so in contrast, these are two contrasting situations. So what the most important physical parameters determine that in your universe for supermassive stars, and in my universe we form clusters.
I have an easy answer, metals and dust.
Just metal and dust.
Yeah, the metals and dust cause the gas to fracture on much smaller
But
mass
you already
scales.
have a lot of metals at Z7, right?
Yes, but the seed formed at redshift 19.
Oh.
Yeah, so that supermassive star that I showed, those two clumps, they were forming by redshift, actually it wasn't even redshift 19, it was redshift 25. And there were no metals in the halo because there had been no prior star formation.
You don't have dust, did you?
There couldn't be any dust, no, because
you
it was,
have no dust, we do.
yeah, exactly, exactly. Dust changes everything. In fact, we have so we're actually working on new simulations now on the cosmological
And
origins
the
of quantum.
density and temperature doesn't matter.
Yes, it does. All of that matters, but it's simple.
Just because metallicity changes everything.
Yes, metallicity, once you get metals and especially dust, the cooling becomes so efficient that you radically decrease the gene's masses.
Any other questions? I have a good question. So then the key issues about for the supermassive star formation is, yes, we don't have metals and we can just build up very huge clump and they collapse. But the key thing is down to the star formation levels, you will eventually have the disk, accretion disk.
Yes.
Then you have a disk instability. That definitely will happen.
Yes.
And that's why I also see in the simulation and ASIAA's other people simulation. So if that fragmentation occurs, that usually will also change the scale of the star significantly.
Mm-hmm.
So maybe fragment a big star, usually you think, oh, just collapse into one star. And then it accrete, and this form and fragment into multiple, maybe a couple of stars, a bunch of stars. So the feedback will also change the accretion because it changes the shuffle the gas reservoir. So I would think if you have a higher resolution, do the simulation again, I guess probably you will see a different result.
Well, so the way to think about that, so this is what Ken's bringing up. Well, and actually I didn't have the time to talk about this. In the initial, I can hop back. Okay, so in these initial stages, here these images capture the initial collapse and formation of those two clumps I was talking about. We had 25 levels of refinement there. There we had a resolution, I want to say on the order of a few AU. And there we could resolve initial disk formation and possibly fragmentation. But here's the problem. We could have continued the simulation at that resolution, but by then our time steps were so short, we could never have crossed 1 million years or 2 million years. That time required to tell us how massive the star would become and at what mass it would collapse. So we had to backstep, we had to back out of that really high resolution simply so we could allow those clumps to evolve for longer times. And that's where we got those large accretion rates that produced the 31,000, 40,000 solar mass stars, seeds at the center of this halo. Now what Ken is saying is, if we had continued to evolve the system at that very high resolution, we would have seen some fragmentation in those disks. And would we have seen just the formation of two really massive stars, or the formation of like a smaller cluster, like a cluster of smaller stars? The shorter answer is we think we would have seen two massive stars, and this is why. The simulations that resolve the fragmentation in those disks show that those fragments coalesce with the central objects on timescales that are shorter than Kelvin-Helmholtz contraction time of the star. So that when fragmentation occurs, most of those fragments still end up in the central object on timescales shorter than the formation time of the star itself. However, it is possible that had we were able to maintain that resolution for the entire 1 to 2 million years, we might have seen the formation of more than one object, more than two objects, but we don't know if they would have coalesced into single objects later because of dynamics or not. And I think that is an open question.
Okay, thanks. Any other comments? Questions? Okay, if not, let's thanks. And again. Thank you.